we have two vectors, v and w, and if you flatten v down onto w in a perpendicular way, you get this dotted blue side here. And we found that the length of the blue side, which we called comp wv, we found that that's v dot w over the magnitude of w. Just as a quick example of this, if v is, say, this formula works in 2D and 3D, but just to have an example in the plane so that it's easy to draw, maybe v is, say, 1, 4, and w could be something like 1, -1. Okay, then the formula for comp tells us that the amount of v pointing in the direction of w is v dot w over the magnitude of w. So v dot w is 1 times 1, so that's the y-coordinate of v times the the x-coordinate of v times the x-coordinate of w, plus the y-coordinate of v, which is 4, times the y-coordinate of w, which is -1, over the magnitude of w, and the magnitude of w is the square root of 1 squared plus -1 squared. And when you work this all out, you get, let's see, 1 minus 4, so -3 over square root of 2. All right. So it seems odd at first that comp tells you the length of v in the direction of w, and we ended up with a negative. So why is it that a length can be negative? Well, if you actually sketch what happens when you flatten v onto the direction of w, like this, what you find is that the part of v in the direction of w is actually pointing opposite w. And that's why this came out negative. Comp comes out negative when the vector that you're flattening points mostly away from the vector that you're flattening onto. Okay, so the piece I wanted to add to this is if you have v and w, just like before, comp tells us the length of this flattened side, but often in applications where you want to flatten one vector onto another like this, you aren't so concerned with just the length of this blue side, but actually what is this bottom side as a vector. So as a vector, this blue vector is called the projection of v onto w. And the notation for it is, well, it's just like comp, except it's a projection instead of a component, so it's called projection onto w of v. And let's figure out a formula for the projection. Well, to figure out a formula for the projection, what we're going to do is use our old trick of writing a vector as the magnitude of the vector times the direction of the vector. That's a trick we've used several times before. And the magnitude of this blue vector, well, that's comp. And comp was v dot w over the magnitude of w. And the direction of the blue arrow, well, since we're flattening v onto the direction of w, the blue arrow has to point in the direction of w. And what is the direction of w? Well, remember, by direction we mean a unit vector, and to get a unit vector in the direction of w, you just take w and divide it by its own magnitude. And so as a result, proj wv is v dot w over the magnitude of w squared times the vector w. And let's take a second just to see that this really does make sense. All of this stuff on this first part, this all produces a scalar, and w itself is a vector. So what we have here is a scalar product of a scalar times a vector, and a scalar product produces a vector. So proj is a vector, and the length of proj is comp, although the comp can be negative if the two vectors are pointing away from each other. All right, so there's this really nice formula that gives you the result of flattening one vector onto another. As an example of this, let's just pick a couple of vectors and see what happens when we flatten one onto the other. Maybe v could be 1, 5, and w, let's say w is, I don't know, how about 2, minus 4. All right, and let's calculate the projection onto w of v. So this is the projection onto w of v. Our formula for it was v dot w over the magnitude of w squared times w itself. So v dot w, that's 1 times 2 plus 5 times negative 4 over the magnitude of w and the squared. The magnitude of w squared is, it's the magnitude formula but without the square root. So that's 2 squared plus negative 4 squared times w itself, and w is the vector 2, negative 4. Oops. Angle bracket. There we go. Okay, so this is, in the numerator, we have 2 minus 20, so negative 18 over 4 plus 16 is 20 times the vector 2, 4. So this is, let's see, let's cancel a factor of 2. We get negative 9 over 10 times 2, 4. And then if you want to put this all into one vector, you get, let's see, we can actually factor another, cancel another factor of 2, make this a 5, this a 1, this a 2, and we get negative 9 over 5, comma, 10 over 5. Okay, so that's what we get when we flatten v onto w. Now something seems to be a little bit funny because this vector that we get, so this is proj w onto v. Now this vector that we got, it's pointing into the second quadrant because its x-coordinate is negative and its y-coordinate is positive. So in other words, it's pointing that way. And that makes me think that this picture is very inaccurate because this picture would make it look like the projection points down and to the right. But that can't be the case because we just calculated the projection and it doesn't point down and to the right. So this picture is not very good. So ignoring that detail, hopefully this gives you an idea of what the projection is calculating and how nice this formula is. This formula is very, very clean. So there are lots of situations where you actually want to calculate a projection, For example, in physics, if you have a force and you need to know how much of that force is tangential or how much is radial, you can just project your force onto the radial or tangential directions.